All right, hello everyone. Let's go ahead and get started here with Kirchhoff's laws and DC circuits. Okay, so by the end of today's lesson, our goals are to get comfortable with applying Kirchhoff's laws to analyze DC resistive circuits. So these are DC circuits containing sources as well as resistors. We're also going to review how to determine equivalent resistance of circuits, so that includes circuits containing resistors in series and in parallel. And we're also going to recognize how to deal with voltage and current sources in series and in parallel. So let's go ahead and get started. First, just a quick review from last time. So in our previous video, we covered how resistors follow Ohm's law. V equals IR. Or if we are time dependent, we have I of t and V of t. We also learned that an independent source is a voltage or current generator which does not depend on any other circuit variables. So independent sources give us the same value no matter what's happening elsewhere in the circuit. We also talked about ideal sources. Ideal sources are voltage and current sources where their behavior does not depend on how much voltage or current is running through it. What we mean here is that these sources can deliver infinitely high voltage or current. They never run out of energy. They never saturate. Of course, in real life, no source is truly ideal. Later on, we'll talk about approximations and other models we use for real sources. So last time we also covered dependent sources. And you'll remember that dependent sources model the situation when one circuit element is proportional to the voltage or current of a second circuit element. You'll remember we gave that water faucet analogy. So if I have like a water faucet or some sort of hose, notice I can have water coming out of my hose. But the flow rate depends on how much we turn the handle. So similarly, a dependent source's output is dependent on some other circuit element. And we learned that we can have dependent current sources as well as dependent voltage sources. You'll also remember I said that you should be happy when you have dependent sources in your circuit, because usually you are given some information about that dependent source. So usually you're given some sort of proportionality constant. And that will help you solve the circuit. This proportionality constant is also known as the gain of your dependent source. We'll take a look at more examples of dependent sources in this video. One last review. Make sure you remember the differences between open and short circuits. Remember, an open circuit is basically like a broken wire or a dead end. We say that an open circuit has zero current, or I equals 0. Meanwhile, a short circuit is basically an ideal voltage source, or equivalent to a plain wire. So if it's a plain resistanceless wire, it's going to have zero voltage across it. Make sure you remember these. We will see that open and short circuits come back in future lectures. So let's go ahead and do another review question before we move on. So I'd encourage you to take a moment and, if you're feeling confident, try pausing the video and see if you can reproduce my solution to this question. So let's go ahead and see how we would approach this. So here we are given a circuit containing a dependent source. And we are asked to determine the value K of that dependent source's gain. So you'll remember here that when we say gain is the proportionality constant. So in the case of the dependent source in this circuit, we see that our source's current is equal to our gain K times I sub A, where in this case, I sub A is the current flowing through our 200 ohm resistor. So you'll remember, if you have a dependent source in your circuit, I mentioned that you should be happy. Because this is free information right here. Dependent sources give us a big hint on how to solve the problem. So in this case, if we want to find our gain K, we need to find K, so we need to determine I source and I sub A. So let's find I sub A and I source, then use them to determine our gain K. So first, let's take a look at I sub A. Well, we know that I sub A is the current through the 200 ohm resistor. But one thing to be careful of here is notice the direction. So if I were to normally apply Ohm's law and use the passive convention, we know that voltage is equal to current times resistance. But you need to be careful because notice I sub A is going in the opposite direction. So in this case, here when we say opposite direction, we mean that it's going against the positive to minus direction of our voltage. Therefore, if we want to use Ohm's law to find I sub A, we need to multiply by -1 in order to reverse our current's direction. So in this case, our current I is actually equal to -1 times I sub A, or negative I sub A. So you want to be really careful of direction here, because we know our voltage, our potential difference would make current want to flow from left to right, but in this case, the I sub A that we depend on is going the opposite way. So because I sub A is going opposite the expected direction, that is why we multiply by -1. So notice, now that we know how I sub A is related here, and we know our resistance is 200 ohms, we can also substitute in our voltage V, which in this case is 10 volts. So therefore we determine that 10 volts is equal to negative I sub A times 200 ohms. Solving for I sub A, we determine that I sub A is equal to negative 10 volts divided by 200 ohms, or negative 0.05 amperes. So we have our I sub A. Now let's find I source. Remember, we know that I source is K times I sub A. So we have I sub A, need to find I source. Well, if we look at our ammeter, notice we are given information about the current. And remember, positive current enters the ammeter's red probe. So the ammeter is telling us that we have 450 milliamps. Notice the direction. We have 450 milliamps entering our dependent source. So what is I source in this case? Well, I source is going the opposite direction. So I source must be negative 450 milliamps, or negative 0.45 amps. Again, the negative due to the current entering, not exiting the source. Remember, if the current is flowing in the opposite direction, then we have to multiply by -1. So notice, now we have minus 0.45 amperes is equal to K times I sub A, which was minus 0.05 amperes. So we can solve for K. And we determine, in this case, that K is equal to, we have negative 0.45 amperes divided by minus 0.05 amperes. That gives us 9. That is our gain. Were you able to get the same thing by doing this yourself? definitely encourage you to try going back through these examples on your own to see if you're able to get the same result. It's very good practice. Let's go ahead and continue on then. All right, so if there's any questions on this material, please feel free to reach out. And now we'll go ahead and continue on to Kirchhoff's laws. So let's face it, in circuits class, circuits can get pretty ugly. And this here is a little bit of an exaggeration. This is a fun comic from XKCD, and you can see there's a pretty ugly circuit here. This one, it's kind of funny. It's got like a sad face, an electric eel, there's a tangle of resistors, lots of crazy stuff going on in this circuit. And so when we see circuits that are ugly, the first thing that the engineer in me wants to do is find a way to simplify stuff. And so wouldn't it be nice if we had some tools to help us simplify and understand ugly circuits? Well, the good news is these tools exist. And during the next few classes, we're actually going to learn a whole bunch of really useful tools. And so our goal is to fill up a toolbox with lots of equations and tricks to make ugly circuits manageable. And as we go through these tools, please make sure you get really comfortable with them. We're going to use these tools over and over again. So one of the most important tools we're going to work with is Kirchhoff's laws. You may remember hearing about these in your electricity physics course. So Kirchhoff's laws ultimately were formulated by Gustav Robert Kirchhoff, and they're based on conservation of energy and conservation of charge. Kirchhoff's current law, which we often call KCL, tells us that the algebraic sum of currents into a node at any instant is 0. So what that means is current is conserved. So the sum of the currents entering must equal the sum of the currents leaving. Kirchhoff's voltage law, KVL, tells us that the algebraic sum of the voltages around any closed loop in a circuit is 0 at all times. So in this case, voltage is conserved. So here when we say loop, remember a loop is a closed path through a circuit, and it does not encounter any node more than once. So what we're saying here is it's a single closed path in our circuit. We're not kind of going over multiple areas several times. Believe it or not, most of the other tools that we use in this course are derived directly from Kirchhoff's laws. So you could say that we're spending most of this course applying Kirchhoff's laws over and over again. But we'll see that these laws can be incredibly useful and powerful. I also highly recommend, whenever you're taking a circuits exam or working on a homework problem and you're not sure where to start, applying Kirchhoff's laws is generally always a good idea. Think about how Kirchhoff's laws can help you get some hints or get an idea of how to approach a problem. We'll do more examples during this video. Here's a few other important things to note about Kirchhoff's laws. First, notice that we say algebraic sum. Algebraic sum means we need to take directions into account. Are we dealing with a rise or a drop relative to something else? Is current entering or leaving? We need to be consistent about which direction we treat as positive and which direction we treat as negative. So for me personally, I like to follow the below conventions shown here. Some students may have learned opposite conventions as this, and that's perfectly okay. You'll notice as long as you are consistent, you should end up with the correct result no matter which convention you use. So whatever convention you decide, make sure you stay consistent when applying it. So I like to use what's called the bank account convention. You can kind of think of it like money in the bank account, right? If money goes into the bank, then that is positive. Just like if current is entering a node, or current is entering, current entering is just like money entering. It's positive. It's entering your bank account. However, if you spend money, or if current is leaving, we treat that current as negative. We use a similar type of convention for voltage sources. For sources, I like to use a positive sign if I encounter the minus end of the voltage source before the plus. Because essentially what I'm doing here is I am gaining voltage. For resistors and other components, so if I have like a resistor, for example, and I'm going across my resistor, remember resistors resist the flow of current, and we have to spend energy in order to pass through that resistor. So a resistor actually will be producing a voltage drop. So if I flow through a resistor and it's the same direction as my current, then I treat that change in voltage as a drop. Let's look at a few more examples of this just to help everybody visualize what's happening. So once again, if I have current entering a node, like node 1, that node is gaining current. Here it would gain plus I1 because current is entering that node. However, node number 2 down below, current is exiting node 2, so node 2 is losing current. We would treat the current leaving node 2 as negative relative to that node. Here's another picture of the voltage conventions that I like to use. So you can see if I am walking across a voltage source and I want to find my voltage in this direction, notice I'm essentially going from an area of low voltage or minus polarity to an area of higher voltage. So I'm treating this as a voltage gain when I walk across the source. It's corresponding to a voltage rise of V1 volts when I walk across my source. In contrast, if I walk from positive to negative of a circuit element, or if I walk in the direction that the current is flowing through a resistor, so again, notice the direction. I'm trying to find voltage in the same direction as my current flow. Notice in this case, I am effectively going from an area of higher voltage to an area of lower voltage. And so essentially here, I will have a negative value, so I will treat this as a voltage drop across that resistor. So once again, this is just the convention that I personally like to use, but if you have learned a different one, just be consistent in how you use it. All right, so before we move on to some examples, I would like to bring up one final point about these bank account conventions. Please note, these conventions should be used specifically when determining the algebraic sum for current or voltage. So you should only really be using these conventions when applying Kirchhoff's laws. So when applying Kirchhoff's current law or Kirchhoff's voltage law to determine the algebraic sum of currents or voltages. So be careful because sometimes students might get confused and think, okay, does that mean when current is leaving my node, the current is always negative? No, these conventions should just be used when determining algebraic sum of current or voltage with Kirchhoff's laws. Let's do some examples of this. So here I have a circuit, and my goal is to write an equation for the current flowing through node A. And so here, if I want to use Kirchhoff's current law, remember that means current is conserved. So the algebraic sum of my currents must equal 0. Well, let's see what's happening. Well, we have I1, which is entering node A. So we end up with a positive current, right? Because since I1 is entering, we give it a positive sign. I2 and I3 are leaving node A. So we write minus I2 minus I3. Finally, we have one more current, I4, which is entering. So we give I4 a positive sign. Those are all the currents that are entering or leaving node A. Just those 4. So we know that the algebraic sum must equal 0. And there's our solution. Remember, it's very important to apply that convention consistently. We always want to give the same sign for current that's flowing in the same direction. Let's try another quick example here. I'd encourage you to pause the video a moment and see if you can figure this one out. Then we'll go ahead and do it together. So here we are looking at node B. We want to use Kirchhoff's current law to write an equation for that node. In this case, we have I1, which is exiting. We have I2, I3 entering. And then we have I6 also entering my node B. So, if we treat current entering as positive, we end up with minus I1 plus I2 plus I3 plus I6 equals 0. So notice in this case, choice B is the correct answer. Covered a couple examples of Kirchhoff's current law. Now let's try an example of Kirchhoff's voltage law. So remember, when we say Kirchhoff's voltage law, that means that voltage is conserved. And so the sum of the voltage rises and drops around any closed loop the sum must be 0. Again, this is the algebraic sum. So the strategy I like to use here is to walk around the circuit. So we want to walk around the circuit and sum the voltage rises and drops. And I'm going to walk clockwise around. In this case, I'm being asked specifically to find Kirchhoff's voltage law around loop number 1, so that's what I'll do. I don't necessarily know what direction the current is flowing. If I did know, generally it's preferable to walk in the direction of the current, but in this case we don't know for sure which way the current's flowing, so I'm just going to go clockwise. And let's apply the convention as we go around our loop. So first we see V3 across a component. And we go from minus to positive. So in this case, we are gaining because we're going from an area of lower voltage to an area of higher voltage. So the first term of our Kirchhoff's voltage law equation will be plus V3. So now I'm about ready to walk through the next component. For V4, notice I am going from a positive across to a negative. So here, I am going to lose V3 because I'm going from high voltage to low voltage. Oh, I'm sorry, not lose V3. I'm going to lose V4 when walking through V4. So I give V4 a negative sign. Next, I'm about to walk across component 5. So notice with component 5, I'm entering the negative end and exiting at the positive end. So I'm going to an area of higher voltage, I'm going to gain V5. And finally, I'm almost back to where I started. I'm about to walk across V6 and component 6. And notice in this case, I'm going from the minus to the positive. So I'm going to gain V6 by the bank account convention. So those are my 4 voltages. So I know by Kirchhoff's voltage law, the sum of all the voltage rises and drops around that closed loop, that sum must be 0. So this is my Kirchhoff's voltage law equation. And you can see in our solution, that is indeed what we end up with. So remember, we want to basically make sure we follow those conventions, both for the sources and the resistors. So typically, in this case, we're going to go ahead and assume that if we are going from negative to positive, we are gaining voltage. You'll also find that had you chosen to use the opposite convention, you would have still ended up with a mathematically identical result. All right, so now let's go ahead and try another example together. I would encourage you to try pausing the recording and see if you can attempt this one on your own, and then we'll discuss. So here we want to write an equation for the voltage flowing through loop number 2. So voltage values for loop number 2. So once again, we can apply Kirchhoff's voltage law just to that loop. And we want to sum the voltage rises and drops around loop number 2. In this case, it appears that my current must be going in a clockwise direction, so I'm going to go ahead and walk clockwise around my loop. If you didn't know which way the current was flowing, you would just pick a direction and start summing. So here, if I start at the bottom of my loop and head toward component 1, we'll see that I first experience the positive and then the negative side of the component. So in this case, my V1, I'm going to treat as negative because I started positive and ended negative. Then I keep walking. Now I'm about to enter component 2. For component 2, I'm starting on the negative side of a voltage and increasing to the positive end. So I'm gaining V2 volts. I started on the negative end and then ended positive. So by convention, I treat that as a gain. So therefore, the correct answer for this question, depending on your convention, you might have gotten either choice C or choice D. You'll notice that these are related by multiplying by -1. Basically, you'd mathematically get the same thing either way. They're equivalent. Basically, if you just move the terms to the other side, you would end up with the same thing. All right, so feel free to reach out if you have questions on this. Next, let's go ahead and cover our remaining topics about resistors. So you may remember learning about resistors in series and parallel in your physics class. If so, you would remember that in a series connection, all elements must have the same current. And that's because the current must pass through one element at a time. And there is only one possible path for that current, through those elements. So in this case, I must pass through Vs, then R1, and then R2, in that order. Right? I have no other choice. I have to go in that direction because those components are in series. So series circuits also are called voltage dividers because they demonstrate a property called voltage division. Essentially, the source's voltage Vs, that voltage is split. It's split across several components or divided up between the resistors. So sometimes series circuits are also called voltage dividers. That leads us to some important equations. So first important equation. If we have a list of resistors in series, such as R1, R2, and R3, we can replace series resistors with a single equivalent resistor, where in this case our equivalent resistor Rs is given by the sum of the series resistors. So here I can replace R1, R2, and R3 with Rs. Rs is just the sum of those series resistors. We also know that the current through a series circuit must be the same throughout, because there is only one path for the current to flow. Therefore, for a series circuit, the current is always going to be given here by our voltage source divided by the resistance of all the resistors in series. This last equation is very useful, and we actually use this a lot in this class. So if we want to find the voltage across the nth resistor in series, we can do so by taking that nth resistor, dividing it by the sum of all the resistors, and multiplying by Vs, where Vs is our source voltage. We'll do an example of this in just a moment. So you might be wondering, well, where did all those equations come from? Believe it or not, all these equations are derived from Kirchhoff's laws. Now, I don't expect you to memorize the derivations, but you can see here, if we were to apply Kirchhoff's voltage law all around this circuit, here the opposite convention was used, but you see that you basically end up with the sum of all the voltages around this loop being 0. And then if we apply Ohm's law, notice how we can combine terms and end up with the equations on our previous slide. Let's also bring up a quick hint that might be useful on future homework assignments. So, an important thing to remember about series resistors is that they all must experience the same current. So notice these two parallel resistors together, and then this resistor here, all three of these sets of resistors can be considered in series with my source. Notice here the parallel resistors would need to be converted to an equivalent series resistor. But once you had determined what that equivalent series resistor is, you could actually add up and say that our equivalent resistance is equal to the sum of those three elements. And remember, the items don't necessarily have to be right next to each other to be in series. We see that these two resistors on the right, circled in red, they are in series with the current source. We see that both of them must experience the same current as our current source. So definitely take advantage of opportunities to recognize when resistors are in series with each other, because it can help you significantly simplify an uglier circuit. Let's go ahead and try a quick example. Suppose we have this circuit shown here, and we're being asked to find the reading on the voltmeter. If you'd like, you can pause the video and try this yourself, or we'll do it together. One thing you might notice is this source. Might be thinking, what's going on? Well, we can actually just redraw this circuit as having a negative 8-volt source. So if you prefer to have your polarity oriented that way, you can certainly do that. Notice all I did was flip the terminals of the source and then put a negative sign in front. So in this case, we want to find the voltage across our 25 ohm resistor. There's basically two approaches we could use here. First approach is we could combine our resistors to an equivalent, then find our current with Ohm's law and solve for our voltage V1. That's probably the approach you'd be familiar with from physics class. Combine the equivalent resistors, solve for current going through, then use Ohm's law to find V1. It's a perfectly valid approach. Another approach is to use our voltage division equation. And in this case, voltage division may save just a little bit of steps. Let's go ahead and demonstrate voltage division. So I'll go ahead and use voltage division to solve this. And remember, for me personally, I prefer to have my sources right side up, so I'm just going to replace my 8-volt current source with a negative 8-volt current source, or negative 8-volt voltage source with the positive terminal face up. Because if I do that, then I can assume my current is flowing in the clockwise direction. And for me personally, that just makes it a little easier because I match the orientation of the voltmeter for the flow of my current. Okay, so let's go ahead and try voltage division using these resistors. So we know that the voltage across the resistor of interest which is in series, is equal to the resistance of that resistor. So voltage of our nth resistor in series is that resistor's resistance divided by the total resistance of all the series resistors times Vs, where Vs is the source voltage. And again, this is assuming the passive convention is satisfied and that the direction is in such that the current is entering the positive terminal. So let's go ahead and plug in then, so we can determine that the voltage across the 25 ohm resistor must be 25 ohms divided by the total, which is 25 ohms plus 75 ohms, times Vs. Vs here is negative 8 volts. Remember, we had to put the negative to make the voltage produce the current in the same direction. So we needed negative sign here just to account for the voltage being flipped in the voltage source. So here I'll just say it's negative to make voltage match the desired current direction. Remember, by the passive convention, that we want the current to enter the positive end. Okay, so we go ahead and solve for our voltage. And we determine that we have 25 ohms divided by 100 ohms times negative 8 volts, which is equal to 1/4 times negative 8 volts, or negative 2 volts. So notice it's very important to pay attention to the polarity and the current directions, because if you're not careful, you might end up making some sign errors. So watch out for those sign errors. And there's our solution. All right, so feel free to reach out if you have questions on that, and we'll move on to parallel resistors. So you may remember from physics class once again that if resistors are in parallel with each other, that means that there are multiple paths that current can go. Current can choose multiple paths, but all the paths have the same voltage drop. So all the paths have the same voltage drop across them. So as you can see here, if I have some voltage, let's call it V1 up there, and V2 down here, you see that no matter which resistor I pass through, both paths experience a voltage drop of V1 minus V2, or both will start at the same voltage, end at the same voltage. In fact, in this case, we can see that that voltage difference will be equal to Vp. So, parallel circuits demonstrate this property called current division because they're basically splitting current across multiple paths. So basically, when we talk current division, what we mean is that the total current across resistors is divided up in a predictable way. Very similar to voltage division. And so you may sometimes hear parallel circuits being called current dividers. Once again, we've got some important equations for those parallel resistors. First, we have that reciprocal equation, which you may recall. So basically 1 over the equivalent resistance of all the resistors is equal to the sum of 1 over each individual resistor. So in this case, for our circuit shown, we'd have 1 over our equivalent resistance is equal to 1 over R1 plus 1 over R2. And if we had more resistors, we would keep summing the parallel resistors. Notice if we have just 2 resistors in parallel, we can use this shortcut equation. But that equation here, R1, R2 over R1 plus R2, it only works if we have just 2 parallel resistors. If you have more than 2, then you have to use the full reciprocal equation. Just like how we had a voltage division equation, there's also a current division equation. So the current division equation is convenient if you have a current source with many parallel resistors. So current division doesn't come up as often in this class, but once in a while it does. Basically, the current division equation lets us find the current across the nth resistor of interest. So we use current division to find the equation across one resistor out of many in parallel. Notice it only works to find the current across an nth resistor in parallel, and all the other resistors must also be in parallel. So this is a fairly special case. But there might be a question about this in future slides or even in a homework assignment. One other thing, this is kind of more just for your information. You can also write a current division equation in terms of conductance. So some textbooks actually like to write current division this way. Remember, conductance G is just 1 over the resistance, so otherwise the equation is the same. Okay, so let's finish up with a few more examples. And so first, let's cover series and parallel sources. So it turns out if we apply Kirchhoff's current law and Kirchhoff's voltage law and Ohm's law, we can derive some equations to simplify when we have multiple sources in a circuit. So if we have voltage sources in series, notice we can combine voltage sources in series. However, notice that you can't combine voltage sources in parallel because that would violate Kirchhoff's voltage law. You couldn't have two different voltages in parallel with each other because if things are in parallel, that means the voltage must be the same. So you have to be a little bit careful with when combining sources. Just make sure that things are indeed in series here before you combine your voltage sources. And if you do combine them, notice depending on polarity, if you have two in series with the polarity matching, then you'd have just directly summing them, so you could just sum VA plus VB. But if the polarities are reversed, then you would subtract the two. Similarly, you can combine parallel current sources. And if I combine parallel current sources, here once again we have IA and IB, we see that if the current is going in the same direction, the current is added. Combine them together to a single source. If the current is flowing in the opposite direction, then by Kirchhoff's current law, we can subtract the opposite from the other direction. Notice we also can't have current sources in series with each other because that would violate Kirchhoff's current law. Because remember, current is conserved, so if you have a single path for current to flow, the current must be the same throughout that single path. All right, so we have just a couple more examples to finish up here. So I would encourage you, if you're feeling confident in this material, you could try these examples on your own. So feel free to pause the video if you'd like. Otherwise, we can do it together. Example 6 asks us to simplify this circuit so that there is just one current source and one voltage source. So here it's important that we need to recognize whether things are in series or in parallel. Well, if I compare the voltage at this top portion of the circuit with the node at the bottom portion, we notice that the 1 amp and 3 amp current sources are in parallel. And if I were to try to walk around my circuit this way, you'll notice that my 2 volt, 5 ohm, and 5 volt components, those must experience the same current. So I can say that my 2 volt and 5 volt source are in series. Therefore, we can combine the parallel current sources and series voltage sources. Just be careful to pay attention to direction and polarity. Let's go ahead and see how we do this. Suppose I were to walk around my circuit. I'm just going to walk around this loop. If I walk around the left loop, notice that first I see something like this. Notice I see the negative terminal of the 2 volts first. And then if I keep going, I will see the positive and then the negative of the 5 volts. You could say that when I walk across the 2-volt voltage source, I gain plus 2 volts, and then when I walk across the 5-volt source, I lose minus 3 volts. Or I'm sorry, I lose minus 5 volts. So therefore, you could conclude, in this case, if I combine those two together, I'm going to end up with my 5 volts minus the 2 volts, I'm going to end up with a 3-volt source. So it will be either minus 3 volts like this, or 3 volts in the same orientation. I can do a similar approach with my current sources. So I see, in this case, I have my 3 amp source, and it's in parallel with a 1 amp source. The directions are opposite. So what I can do in this case is I can say that I have a 3 amp minus 1 amp, or a single 2 amp source pointing upwards. So therefore, if I go ahead and crunch all the numbers, you see that's indeed what we get. We get a 3-volt source up top, because we subtract the 2 volts from the 5 volts, and then similarly we subtract the 1 amp from the 3 amp to get the 2 amp current source. All right, we have just one more example to go. In this example, I think the circuit on the left is a little bit ugly. And I want to replace the resistors on the left-hand side circuit such that there is a single equivalent resistor. So I'd encourage you to go ahead and pause the video and give this a try, and then we'll discuss. So the important strategy for this type of question is to make sure you recognize which resistors are in series versus in parallel. Let's give it a try. So first notice that the 40 ohm and the 10 ohm are in parallel. So I can use my shortcut equation. We know that if I have two resistors in parallel, I can use this notation, R1 parallel R2. We know that two parallel resistors can be replaced with an equivalent resistor, where the equivalent resistance is R1, R2 divided by R1 plus R2. So in this case, that will give us 40 times 10 divided by 40 plus 10, which is 400 over 50, or 8 ohms. So already we've simplified down a little bit. We have a 12 ohm, an 8 ohm, 4 ohm, and 12 ohm as our resistor piece of our circuit. So notice that after getting rid of those two parallel resistors and replacing with the 8 ohm, we can now combine the 4 ohm and 12 ohm on the upper path because those are in series. And we can combine the 12 ohm and the 8 ohm in the lower path because those two are also in series. So if we do that, again, we have a 4 ohm, 12 ohm, 12 ohm, 8 ohm. This will become 16 ohm in parallel with a 20 ohm resistor. So if we have a 16 ohm in parallel with a 20 ohm resistor, well, we can once again use the shortcut again. It will be 16 times 20. 16 times 20 because 16 is parallel with 20 over 16 plus 20. That's 3200 divided by 36. Or you could also write by 800 divided by 9. 800 divided by 9 gives you about 88.89 ohms for that equivalent resistor. All right, so there you have it. Make sure you start getting comfortable recognizing whether things are in series or in parallel. It can make simplifying circuits a lot easier. And there we have our solution. All right, so once again, just to wrap up for today, you should now be starting to get more comfortable using Kirchhoff's laws and parallel and series resistors to simplify our circuits. So please make sure you understand these key points because we are going to be using these laws and these tools extremely often in our class. In the next video, we'll start looking at even more tools, including node and mesh analysis. Feel free to reach out if you have any other questions, and we'll see you in the next video. Thanks, everyone.